Okay, we're ready to get chapter 4 started here. So the first section is vector spaces and subspaces. So chapter 4 is all about vector spaces. Now, vector spaces share a lot of overlap with the things we've talked about. Okay, we've already talked about vector equations. We're using a lot of the same ideas. We use linear combinations. We use linear independence. But the reason for vector spaces is we can broaden our field that we play on here. We've talked pretty exclusively about systems of equations. X1 v1 plus x2 v2, however many vectors we have, end at xn vn, and that's equal to some b, or maybe it's equal to 0 for a homogeneous. In our vectors here, we're purely just lists of numbers, right? So, A, B, C, D, however many points we have. Okay, so the idea behind a vector space is that we can take these setups and we can use these setups on different looking types of vectors. Okay, maybe a vector looks like a polynomial. Maybe a vector looks like a matrix itself. Okay, we can apply these same structures to these ideas. Okay, so first we're going to need some criteria for sorry. So first we're going to need some criteria for our vector spaces. Okay, so to be a vector space, you have to meet 10 criteria. Okay, now most of these are fairly straightforward, okay, and we kind of get by default, and they make it seem like the space is normal. It's there's nothing strange about it. In other words, okay. So condition 1: if I have u and v that are in my vector space V, so let me put that first. For a vector space, try this again. For V, I have to start over on that writing, sorry. For V to be a vector space, there we go, that'll work. For V to be a vector space, if I have two vectors, u and v, that are in my vector space V, okay, so these are vectors. Okay, I'm not going to bold them every time I write them here, but just to emphasize they're vectors. Okay, then u plus v is in V. Okay, as expected. Okay, u plus v has to be in V. Okay, condition 2: u plus v has to equal v plus u. Okay, so we want it to be commutative, just like we're familiar with vectors to this point. Okay. Condition 3: I need associativity. U plus v plus w should equal u plus v plus w. Okay. Condition 4: there is 0 that's in my space V, such that 0 plus v, little v that is equal to v. Okay, so a 0 vector, that when you add the 0 vector to v, you just keep the same number. That makes sense. That's a normal operation for us. If we add 0, we should still get 0. Okay, 5, there is negative u for any u in v, such that negative u plus u is equal to 0. Okay, so we have an additive inverse. Okay, so you can think of these, right? This is closed under addition. This is commutative. Associative is number 3. I have a 0 property. Okay, I have a 0 vector, something that adds no quantity. And I have a additive inverse, something that when I add it to a negative u, to its counterpart, I get 0. Okay. Condition 6 is that if u is in V and C is a scalar, then CU is in V. Okay, so it's closed under scalar multiplication, something we're familiar with from our previous sections. Okay, condition 7, I have scalar associativity, or scalar distribution. So C times U plus V is going to equal to CU plus CV. So I can distribute that scalar. Okay, and then I have vector distributivity. So I get that if I have C plus D times U, that's the same thing as CU plus DU. Okay, 9. If I have C times DU, that is the same thing as doing CD times U. And then the last condition, that there is a multiplicative identity. There is some 1 times U that is equal to U. Okay? Now, you'll notice all of these conditions are relatively normal conditions just for using any kind of space. We're very accustomed to that relationship. Okay? There's nothing too difficult to deal with there. Okay? So let's look at a couple of examples of some vector spaces. Now, our most common example is the r to the n power. Okay, you know, R2, R3, R4. Those are our most typical, our Cartesian grids, right? Because we know that when we add real numbers, it's associative. We subtract real numbers, it's associative. We know that it's commutative operations. You know, all the things we know about real numbers clearly cover these 10 criteria up here. Okay, so our real numbers are our most common vector spaces, and they're what we deal with the most often. Now, within these vector spaces, many subsets of Rn are also vector spaces. Okay, so remember the title of the section was vector spaces and subspaces. So I said vectors and not vector spaces. There we go. Many subsets of Rn are also vector spaces. Okay, so vector spaces and subspaces. So as we look through here, we're going to look at what makes a subspace, okay, as opposed to just a subset. Okay, because you can be a subset of Rn real easily, but it may be more difficult to be a subspace. Okay. Remember the same idea when we talked about homogeneous and non-homogeneous systems. The solution to the homogeneous that always went through the origin, it was a subspace, but if I shifted it up, then I didn't have those scalar multiples. Okay, I didn't get those. Okay. So there are lots of examples we can use of a vector space. Okay. Geometrically, right, I can think of some type of, you know, grid here where I have a parallelogram rule, right, that we're familiar with. Okay, so I have maybe a vector u and a vector v. And I can have some corresponding parallelogram rule that's going to keep my sums inside here. You know, I could create a grid that doesn't use coordinates to map in here, okay? But I have something where this is the entire space, so I can create a rule for putting u with v. I can stick things together accordingly, okay? Now, if you start going with a coordinate system, right, you get where you can bring it outside, things like that. So if you limit your space, you can turn that into a vector space, okay? Another example, okay, is that I can have infinite dimension type things. I can use sequences. If you remember sequences from calculus, hey, I could have a sequence that is x1, x2, x3, ... that continues, xk. Okay, so that's a finite one. Okay, if you think about the numbers here, if these are all real numbers, well, when I do my operations on them, this behaves basically exactly like Rn, or Rk in this case, since I stopped at k. Okay, but also I could do it infinitely in an infinite fashion. So let's call this one xk, and I'll make the numbers inside a1, a2, and that just continues indefinitely. It's infinite. Okay, well, think about if I add numbers here, I could add them in either order. I could do it associatively. I could pick 3 different ones and arrange them. When I still add them up, I'd still get just the sum of the 3 vectors that I chose. If I have all zeros, if I add that to a coordinate, I get the 0 vector. Okay? I could pick a negative one. Well, what would the negative of xk be? It would just make all of the values before negative. And that pattern would continue indefinitely. Okay? I could multiply it by a scalar. That would give me CA. It would still be in there. So as long as I don't restrict these A's, okay, as long as I just say AI is an element of the real numbers, ultimately this just behaves exactly like R. It's a bit like an R infinity, okay? And we don't really use that space. We don't really have that space, but it's what it behaves like. So it's just like a multiple of Rn. Okay, it's just like a version of Rn. You know, we can add, subtract, we can do associative, we can multiply by a scalar. There's a 1 vector where I just make everybody 1. Okay, and 1 times xk will still be xk. Okay, so we can have infinite dimensions now for a vector space. Okay. Now, two big ones here are polynomials. Okay, and we think, well, polynomial is not a vector, and that's true to some extent. So we're going to have a polynomial p of t that's going to be equal to a times t to the n power plus b times t to the n minus 1 power plus c times t to the n minus 2 power. Remember, we talked about how this weren't linear equations, which is a true statement. This is not a linear equation. It has powers, has different things going on, and that goes all the way down to some ending constant. Okay. Well, I could think of this as looking like a vector. And this vector would have the coefficients, a, b, c, all the way to z. Okay? And I can think about when I add two of these polynomials. So let's call this p1 of t plus p2 of t. When I add those two polynomials, what do I get? I simply get that p1 would be a1 plus a2. If I add that together, I still get a coefficient times t to the n power. And if I add the n minus 1 powers, I get a coefficient times n minus 1. Coefficient times n minus 1. Okay, so this clearly is still an element of this space. Okay, and much like we represent reals with R, we use this blackboard bold P, Pn to represent these polynomials. Okay, so if I have P2, the elements of P2 are AT squared plus BT plus C. Okay, it just stops at squared. This would be like P26 because I have 26 going all the way down to Z. Okay, so we have to have somewhere we start and stop. We don't have a P infinity. All right, we have a highest power. The degree of the polynomial given there is n. Okay. All right, so that would be P2, P3, right, would start at cubed. I could have a subset of P2, maybe that's just AT squared. So B and C have to be 0 all the time, okay? But this would be a subset, and let's think about what happens. If I add vectors here, I just get 0 and 0 out on the other side. I'll get a coefficient times t squared. If I do them in reverse order, I still get the same coefficient. If I do associativity, I still get the same. I can make A be 0. Look at those 10 criteria and think through which ones are met, okay? Now, you're not going to have to prove all 10 criteria. You're not going to have to go through and write out as something that says, okay, criteria 1 is true because of this, criteria 2 is true because of this. You're just looking for one that fails, okay? So most often the one that would fail would be the zero condition, the fact that you have to have a 0 vector. So if I take the subset now and I make it AT squared plus 1, well, there's not anything that's 0 that's in this space. I can make A 0, but then I'm still adding 1. Okay, so to continue this example, I'm going to go over the next page. So continuing this example here, if I have AT squared plus 1, okay, and I'm asking, is this a vector space? Hey, is this a vector space? Well, in order for that to be a vector space, I need it to have 0. So if I do a t squared plus 1, okay, well, the only candidate I could possibly have to be my 0 vector would be 0t squared plus 1. Remember, the plus 1 has, in order to be in this space, you've got to have that plus 1. But when I add those, I'm going to get a t squared. That part's good, but then it's going to be plus 2. And plus 2 is not in my space V. Okay? So is this a vector space? No, because the 0 vector is not in that space. So the 0 vector is that most important condition that kills a lot of these vector spaces and goofs them up and messes them up and things like that. Okay? All right, so we want to talk about being a subspace. Okay? So AT squared is clearly inside of P2, right? AT squared plus 1 is clearly inside of P2. But plus 1, so this is the symbol for is a subset. This is a subset of all the polynomials that are at degree 2. But plus 1 makes it not a subspace, okay? So it's not a vector space, so we surely don't want it to be a subspace, okay? So not a vector space, no vector space. So by extension, it's not a subspace. Okay, but we said AT squared on the last one. Well, that's a subset of P2. Again, everything in there is inside of P2. It's just where all the B's and C's are 0. Okay, well, that is a vector space. Okay, so if I have a vector space that's a subset, we want that to be a subspace. Okay, now, since it's a subset, we can boil down those 10 conditions. Okay, so simply put, to be a subspace, so a subspace H of V is a vector space and H is a subset of V. Okay, those are the two big overarching criteria. Okay, now since it's a subset, okay, we get a lot of the conditions that we had to show for V for free. Okay, we get most of these things for free. There are just 3 big ones. Okay, so our subspace conditions: 1, 0 has to be in H, and 0 has to be the same as 0 for the bigger space V. Okay, so you'll know what the 0 vector is for V. It's usually pretty easy to determine. Okay, then you have to use that same 0 vector in H to show that it is a subspace. Okay. 2, H is closed under vector addition. Okay, so U plus V is an element of H if U and V are elements of my subspace H, or my possible subspace H. And then 3, H is closed under scalar multiplication. Okay, now this is the other big one that trips us up. So CU is in H if C is a real and U is in H. Okay, now this is the other one that trips us up, because many times if I multiply by a negative, that may throw me out of my space. Okay, that's the most common thing beyond the 0 vector that gets us. Okay, so let's look at some examples. Okay, I have the 0 vector. The whole space is just the 0 vector. Well, if I add the 0 vector to the 0 vector, I get the 0 vector. If I multiply it by a scalar, I still get the 0 vector. This is a subspace of anybody. Okay, remember that one of the conditions is that the 0 vector has to be in that space. I have to have a particular vector such that when I add it, I get the same thing. U plus 0 is 0. Well, in this case, 0 plus 0 is 0. I'm all covered. So if you just have that one vector, you know that's a subspace, okay? All right, V is a subspace of itself, okay? V meets all the criteria. So it's all, and remember, any set is a subset of itself. It meets those criteria 1 through 10. We know that those 3 subspace criteria are some of those criteria. So it's got those covered. So it's a subspace of itself. So for any space, we always have at least 2 subspaces. Those 2 subspaces are just the 0 vector and itself. We probably have others, but we have at least those, okay? All right, let's look at another here. Okay, this subspace H, or possible subspace H, is vectors of this form, where S and T are real numbers. Okay, so it's S, T, and 0, where S and T are real numbers, okay? So H would be a possible subspace. Is it a subspace of R3? Okay. So let's go through the criteria one at a time. So these are clearly in R3. These are R3 vectors. They have 3 coordinates. So the first coordinate, right, 0 needs to be an element of H. Okay. Well, 0, 0, 0 is an element of H. Okay. Since 0 and 0 are elements of the reals, right? Because I need S and T to be real numbers. So they're clearly real numbers. Okay. Condition 2, if I add S1, T1, 0, S2, T2, 0. Okay, we add vectors component-wise, right? So S1 plus S2, T1 plus T2, 0. Well, S1 plus S2 is a real number because S1 and S2 are real numbers. T1 and T2 are real numbers. So when I add them together, I get real numbers. So condition 2 is a check. Okay, how about condition 3? Well, condition 3 is a scalar, right? So if I do C times S times T times 0, I get CS, CT, 0. Well, CS and CT are both real numbers. So it meets the criteria to be in this space. So I've checked all 3 subspace criteria. This is a subspace of R3. Okay, now where it can get confusing or where it crosses people up, right, is if I change this example now, just ST. Okay, so I now have just 2 coordinates, but my vector now is in R2. Okay, well, if you go through here, you could get 0 and 0, ignore the third 0, right? That's still the case here. All the same criteria apply, you just don't have this 0 along the bottom, okay? Well, this is a subspace, meets the criteria basically the same way, but it's a subspace of R2. Okay, it's not a subspace of R3. Okay, it's not a subset of R3. These vectors are in R2, they're not in R3. Okay, the vectors up here were in R3, not in R2. So the question comes up, well, is R2 a subspace of R3? That answer is no. Okay, they're both interesting subspaces and they have interesting results, but R2 is not a subspace of R3. And the reason is because that it's not a subset. Now, there are behaviors that are similar, right? If you think about your Cartesian plane, you know, you think about what a Cartesian plane looks like in R3, you know, or maybe you have your X, Y, and Z axes, okay? Oops, sorry, camera around there. You have your X, Y, and Z axes, okay? Well, this plane here, this XY plane, where all the Z's are 0, looks a lot like R2. Looks basically exactly like R2, but it's not R2. It's still a plane in R3. Now, it behaves identically, but it's not R2 itself, okay? So this picture is this space H that I wrote up before, this ST0, because it has all the coordinates here in the XY plane, right? And it has no height on the Z-axis, but it's not R2. It's R3 still, okay? It's a subspace of R3 that looks like R2, but it's not R2, okay? And so similarly, R4 is not a subset of R4, R5 is not a subset of R4, right? They got those dimensions, right, have to match up. Remember, the dimension was the number of vectors at a basis. So if you're in R4, right, you've got 4 basis vectors. If you're in R3, you've only got 3 basis vectors. Okay, so those bases have to match up. Okay. All right. So we know about subspaces now. We know about vector spaces. We want to relate this to our concepts that we've got already. Okay, so let's go back to that example we were just looking at. I've got H that's equal to the set of all vectors where I have S, T, 0, where S and T are real numbers. Okay, S and T are real numbers. So I want to find a basis for H. Okay, and if I'm looking for a basis for H, I'm looking for what's called a spanning set. Okay, because remember what it has to be a basis. It has to cover the whole space, okay, and the vectors have to be linearly independent. So linearly independent is going to be my spanning set, okay? So let's look at this vector. I have an S component for the vector and a T component for the vector. Okay, well in S, I have 1 copy in the first position, no copies and no copies after that. For T, I have 0, 1, and 0. Okay, well the span of these 2 vectors, and you should recognize these 2 vectors, they're the identity vectors, right? The span of 1, 0, 0 and 0, 1, 0 is equal to H. Okay, and the other reason that a spanning set is important is that if you have a spanning set, you have linear combinations, right? Remember what span would mean. If I call this V1, I call this V2. This means that X1 V1 plus X2 V2 is an element of that H, okay? Because I have all the linear combinations, okay? So the span then is covered. So if you can find a spanning set, you've proven that it's a subspace, okay? Because span gives you all of those properties, gives you all 3 of those properties for free, okay? Span and linear combinations together. So if you can find a spanning set, then you are covered, okay? So a spanning set is the easiest way to find whether something is a subspace. Okay, let's look at another one here. Okay, A, B, and C are real numbers. I have 2A for the first coordinate, 3B plus C, 2C, and 0. Okay, so I'm looking for that spanning set. Okay, that spanning set, well, I look here, I've got 3 components, A, B, and C. Well, my first one, right, is going to cover vector A, 2, 0, 0, and 0. Right, I get 4 coordinates. This is a subspace possibly of R4. Okay, and then I've got 0, 3 for B, because now I'm on B. No B's in the first spot, 3 B's in the second spot, no B's in the third, 0 for the fourth. And the fourth then is no copies of C, 1 copy of C there, 2 for the third one, and 0 for the last one. Okay, so it's pretty easy then to write down your spanning set if you have this type of representation. Okay, well, what if I go to P2 is AT squared plus BT a subspace? So remember, we said for P2 that the vectors there looked like, I could think of these as vectors with A, B, and C. where you had AT squared plus BT plus C, okay? So we're asking if this is a subspace. So my spanning set vectors, well, I'm going to have A covered and B covered. Okay, I don't have C. If I add, I still get the zero vector. If I can mix them around, I still get things that work out. Okay, so I can switch these polynomials into vector notation and make it a vector space because I can find the spanning set vectors. Now, remember, these are polynomials. So really, 1, 0, 0 is the same thing as AT squared, and 0, 1, 0 is the same thing as BT. So really, those are my spanning set vectors, okay? Just using the vector notation to determine what they look like, okay? Now, I can also do matrices, okay? So I have M, this Blackboard bold M, 2 by 2. This is the set of all 2 by 2 matrices, A, B, C, D, okay? Well, you can imagine then I can make this look like R4 using A, B, C, and D, and then I can apply all the same properties to it, okay? So your basis vectors here would be 1, 0, 0, 0, right? That's 1 for A. 0, 1, 0, 0, that's 1 for B. 0, 0, 1, 0, that's 1 for C. And 0, 0, 0, 1, that's 1 for D. So we can turn these matrices into vectors and think of it as a vector space. Okay? So we have matrix spaces, we have vector spaces, we have polynomial spaces. Okay, remember Rn is not inside of Rm. Okay, we can also use this same ideas to help us figure out that something isn't a vector space. So let's say H then is A, B, 1, 0. It's 2 by 2 matrices. Okay, where A and B are real numbers. Okay, A and B are real numbers. Well, the problem here then is that the 0 vector is not an element of H because of this 1, right? You could also do it by checking addition, right? If I have AB 1, 0 plus A2, B2, 1, 0, because it's got to be 1 and 0 to be in H, and when I add those, I'm going to get A plus A2, that's fine. I'm going to get B plus B2, that's fine. But then 1 plus 1 is going to be 2, which is not in H. Okay, so that 0 vector kills it off a lot of the time. Okay. Now, another thing that could happen to you is you can look at odd numbers and even numbers. Okay. Well, let's say H is equal to 2A, 2B, and 2C. Okay. So those are even numbers where A, B, and C are elements of the reals. Okay. These are all even numbers. If I add even numbers, I get more even numbers. But I could have a different H, let's call it H star, where now these are odd numbers, 2A plus 1, 2B plus 1, 2C plus 1. When you add up those odd numbers, you may get even numbers, okay? So remember that the sum of 2 even numbers is still an even number, but the sum of 2 odd numbers is not. So this one is not a subspace, where that one is a subspace. Okay, and you could write your basis vectors here, right? 2, 0, 0, 0, 2, 0, 0, 0, 2. Okay, sum of 2 even numbers is always even. The sum of 2 odd numbers is not always odd. In fact, sum of 2 odd numbers is never odd. And sum of 2 odd numbers is always even. Okay. All right, so that's a intro to vector spaces here. You can have several different things that complicate it, but if you get something that those 3 main conditions, right, for subspace, the 0 vector has to be in the space, it has to be closed under addition, it has to be closed under scalar multiplication. Okay, so that's going to be the end of section 4.1 for us. Okay, we will keep going with vector spaces and subspaces. We'll relate it to a lot of the things we've already talked about, right? So 4.2 is null spaces, column spaces, and linear transformations. again, for these vector space ideas where we're able to broaden our horizons and not just deal with vectors that are in R2 or R3 or R4 like we have to this point. Okay. If you have any questions, please contact me. I'd be happy to help you. Make sure you're staying on top of those homework assignments, quizzes, and tests, and so forth. Again, if there's any questions, whether it's about linear algebra or about the course format, I'd be happy to help you. Okay, and I'll talk to you in 4.2.